So let's continue with this story of trying to solve these second order differential equations and comparing what we get. Uh, on the PDF, number 3 is just doing the case where lambda equals 0. That's really easy. And that can lead in a different direction because it's an interesting special case, but it doesn't lead towards the complex numbers. So I'm going to skip it. Y double prime equals lambda y, lambda less than 0. That's going to be the really interesting case. Well, so far we've gotten pretty far by just guessing the answers. Okay, well, if we tried to guess y of t equals e to the plus or minus root lambda t, seems like we're out of luck because we try to take the square root of a negative number. Okay, now, of course, we'll come back to that, but let's not be so ambitious as to, or so desperate as to try to invent stuff, invent new mathematics right now. There's a much better guess because we know functions that have this property. For example, if lambda is negative 1, we're just looking for a function that when you take two derivatives of itself, it's exactly the negative of what you get, what you started with. Well, we know two functions that have that property. Y of t equals cosine t. I'm going to leave a little space. And y of t equals sine t. Now, if we want a lambda to come out, we're taking two derivatives. So if you put a root negative lambda here, root negative lambda. Okay, that didn't fit. I didn't leave enough space. Okay. Then what's y prime? That's going to be minus root minus lambda sine root minus lambda t. And y double prime, still working for the cosine, is minus and then root minus lambda squared. If I multiply that by itself, you get minus a minus lambda cosine root minus lambda t. And indeed, that's what we wanted. That's just lambda times y. Okay, so we did know things after all, functions that seemed totally different and totally unrelated to the exponential solutions we were getting both for the first order equation and for the case where lambda is greater than 0. So, okay, what's the problem, right? It's just different, right? Well, it'd be wonderful to have a unified theory here. In particular, it'd be really nice to have a unified theory. Remember, what we really want to do is equations like this. Okay. And it's not at all obvious that we could guess the answer to this, and we can't. Well, if you're a really good guesser, okay. And it seems a little bit unlikely that we could really get some traction on here unless we can figure out some more about how this thing works for all different lambdas. And that's exactly what we're going to discover, that's incredibly useful. Okay. But let's keep running with this. Okay. We know for B, this question I've asked before, if I have these two solutions, can I create more? Is it just these two special functions? Of course not. It's still a linear equation. And so I can combine them with arbitrary constant coefficients. Of course, really important that I use constant coefficients. Oops, squeeze it in. Because otherwise the derivatives will start doing complicated things. But if they're constants, derivatives don't do anything complicated. Okay, so and that's the general solution to this equation, just accomplished by guessing. Okay, now let's emulate what we were doing before with the lambda positive case. In particular, to be really specific, we'd like to look at, and this is what I call part C, what if we have like y double prime equals lambda y, and we have pure motion. Let's say why not? Why not? I guess I used 1 before, but it doesn't matter too much if I just put in an arbitrary number there. Oh, it's kind of slanty. Sorry. Okay. There, fixed. So that's going to be where we just need the cosine and no sine. Y of t is y naught cosine of root minus lambda times t. Because that's going to give y naught, and when you take the derivative, the sine is just going to be 0 when t equals 0. Okay, so this is really it's really not a bad way to think of the meaning of the cosine, or one of the deepest reasons why you'd be interested in the cosine function is that it solves this problem. An incredibly important, simple, linear very natural second order differential equation with pure position initial condition, no motion. And if we do pure motion, y prime of 0 equals, let's say, v naught, then y of t, it's just slightly more complicated. It's going to be the sine, because the cosine would screw this up. And it's going to be y naught. Pause it if you want to do it yourself, please. That's really much better than just passively listening to this. I don't want to keep saying that, it's going to get really old, but really, pause it. Look at the PDF. Do it yourself. Okay. So with that, with just a little bit of fudging in the numerical coefficient, that's the role of the sine function. And of course, if lambda happens to be -1, then this actually is just exactly, ooh, that's a v naught. Haha, did you catch that? Good for you. So this is what the sine function it really exists for. This is one of the very, very basic versions of the sine function. Why it's so important. It solves this second order differential equation with pure motion information. Now note the similarity between this stuff and the Cauchy-Cinch story, the hyperbolic cosine and the hyperbolic sine story. Now there does seem to be a similar story, although partly it's because we called it hyperbolic cosine and hyperbolic sine, and if we haven't really justified that yet. But there really is a similarity here, even though there doesn't seem to be a similarity. We don't understand if there's a similarity yet between cosine and sine and exponentials. Okay, so that's really suggestive that there should be something here, some sort of unity. But the last question I ask, part E, is let's compare this to problem 2. That's with the Cauchy-Cinch. Do the actual solutions qualitatively, like graphically, look similar? Well, not really. You know, these guys look like wiggles, whereas Cauchy-Cinch looked like these guys. This had at most one critical point. There was no idea of turning around over and over and over and over again. These guys were not bounded. This guy's bounded. That suggests that we're foolish to think that we could unify these, and maybe this is just a very misleading similarity. Okay. Although it does remind us that the fact that the solution is bounded, that is really, really nice for a physical system. And of course, this is the first time we've actually got something. Scoot this up here. This could be y double prime plus ky equals 0, where k is negative lambda, and therefore would be positive. This really is the motion of a spring with mass 1, spring constant k equals negative lambda, positive. This is simple harmonic motion, cosines and sines, just bouncing up and down forever. This is the first thing it's physically somewhat reasonable. Of course, only in a perfect world. In our imperfect world with friction and damping, it would eventually die off. So it's kind of disappointing that we've finally gotten to something that's pretty close to realistic, and yet it seems to totally break the nice pattern with the e's. Okay, so let's think about that. So this is problem 5 on that part 1 PDF. I'm going to give a big hint. I mean, I really hate to give things away, because I really try to emphasize that with small hints, you can figure out a lot of this stuff on your own, just by asking usually natural questions. Well, here's a big hint. We're going to graph the two separate solutions, sine and cosine. Instead of adding them to be one function, I'm going to make them the x and y coordinates of a point moving in the plane. So that's probably not something most people would guess to do, but it's going to be really useful. Okay. So in other words, we're going to look at, and let's set lambda equals -1 to be simple. So here's the simplest pure position initial condition. We'll call that x, and that'll be the x coordinate of a moving point. And this will be our usual y. Okay, that's as simple as we can get. Okay, and of course, we know that this was the simplest case of our guess. This is cosine and sine. And unless you know very little about cosine and sine, we know you know that it's really good to plot these in the plane. Okay, so that's something that's not too unreasonable. This starts at 1 comma 0, goes around on the unit circle in a very steady motion around the unit circle. Well, so what, right? We kind of knew that. Cosine and sine are supposed to be, that's another, of course, incredibly good role. That's one of the first roles you usually see about cosine and sine. Usually you're not introduced to cosine and sine as solutions of differential equations, right? You're introduced to them in terms of triangle trig or circle trig. Here we go. If this angle is t radians, or in other words, this arc length is t, then this is cosine t comma sine t. And it goes around in a steady motion forever and ever and ever. Well, that's actually a really, really big hint that maybe there's something to this. Okay. Remember that the exponential function never stopped and turned around. And with one exception, we didn't find any turnarounds for Cauchy Cinch either. Exponentials just progressively do the same thing over and over again. They grow in the same steady fashion in terms of progressive, constant relative growth. Well, it didn't look like cosine and sine were doing anything steady. It looked like they were vacillating, changing their minds infinitely often. But if you put them together and put them in the plane, suddenly it's progressive steady motion, not in the same direction, not blowing up to infinity, going around, but it's still steady motion. That's really cool. Okay, that's a big hint that maybe not only is this a somewhat good idea, this might be the key to everything, to put these together in the plane. Okay, now, makes sense to think about, what if we did that with the Cauchy Cinch thing? It's not going to be the focus of what I'm talking about, but it's really cool, and it may or may not be, even if you've seen hyperbolic functions, even maybe a little bit, you may not have seen this. Well, hopefully you would have. Okay, what if we switch back to plus? So here's the pure position initial condition problem, initial value problem, for the plus sign version. Here's the pure motion version. Okay, and of course we know this was e to the t plus e to the minus t over 2. And this is e to the t minus e to the minus t over 2. Okay. So if we plot that, now again, this depends on how much you know about hyperbolic functions. I could do a digression. Oh, that's x. Sorry. This is a parametric curve in x and y plane. Really good place to stop and try to figure out from scratch what this curve does. There's various more or less high-tech ways to do that. If you just want to plug it into a calculator, that's not so bad. But you might already know that it does this. It traces out one branch of a hyperbola. It traces out this branch of the unit hyperbola, like this. Okay. And that's quite different. In some ways, that's quite different from tracing out a circle. But, wait a minute. They're both conic sections. Okay. These guys, let's see if we put them together. Okay. These guys have very similar equations that define them just by flipping a sign. This is x squared plus y squared equals 1, and this is x squared minus y squared equals 1, which, again, is a good exercise to verify that if you take this squared minus this squared, you get 1. It's not very hard algebra. Okay. So, it turns out that that's another hint. Okay, yes, there's things that are different about these cases, but they're both conic sections. These are both, when you put them in the plane, this traces out a certain conic section, a hyperbola, although only one branch. There's some subtleties to that. And this traces out a circle. Okay, maybe we're not so crazy to think that these guys could be unified. Okay, we'll finish up part 1 in the next video.